In this question we're going to find the inverse Laplace transform of f of s. Now here we've got 3s plus 2 divided by s squared plus 5s plus 4. Now before we go on to take the inverse Laplace transform, we need to check what we've got in terms of this fraction here. So we'll let p of s equal 3s plus 2, and we'll let q of s equal s squared plus 5s plus 4. So that's our starting point. Now what we want to do is find the limit as s approaches infinity of f of s. So the limit as our degree of p is 1 less than the degree of q, this limit will equal 0. So therefore we can go ahead and break this down into Laplace transform, the inverse version of it, by using partial fraction decomposition. So next what we need to do is to try and break this apart. So s squared plus 5s plus 4, we know we can factorise our denominator, so this will become s plus 4s plus 1. So that's a reasonably straightforward factorisation. S plus 4 times s plus 1. So now let's rewrite our function f of s in terms of our q of s being factorised. So now we've got 3s plus 2 divided by s plus 4 times s plus 1. Okay, now partial fraction decomposition. That's going to take the form of a over s plus 4 plus b over s plus 1, with a and b being coefficients that we now need to find. Now the method I will use for this is the Heaviside cover-up method. So what we'll do is we'll write our function in terms of our a. So a will equal, and then what we'll do is we'll make this s plus 4 disappear, i.e. become 0. So then that will mean s is minus 4. So then we write this side with this one covered up. So 3s plus 2 divided by s plus 1, and evaluate at s equals minus 4. So that will give us 3 times minus 4, that's minus 12 plus 2, and minus 4 plus 1. So then that will give us a equals minus 10 over minus 3, which is 10 over 3. So we do the same for our b. So b will equal 3s plus 2. This time we want the s plus 1 to be evaluated when s plus 1 is 0, so i.e. when s equals minus 1. And then as that one disappears, we'll write this f of s without that fraction in the denominator. So then we've got s plus 4. So we don't need the bracket, I'll just write s plus 4 and evaluate at s equals minus 1. So we can go straight in with this. 3 times minus 1 is minus 3, plus 2, that's minus 1, and minus 1 plus 4, that's positive 3. So our our b is minus 1/3. So now we've got this far, we'll rewrite our f of s with this partial fraction decomposition taken care of. So we've got 10 divided by 3 times s plus 4 plus b. Well, b is a minus, so I'll put a minus sign in there. 1 over 3 times s plus 1. Okay, so that's our f of s. Now, what we want to find out is the inverse Laplace of this. So this is what we're looking for. So the inverse Laplace of f, that will equal the inverse Laplace of this here. So it's 10 over 3 times s plus 4 minus 1 over 3 times s plus 1. So that's our goal. Now, with the linearity of Laplace inverse transforms, we can break this apart into 2 separate fractions. So let's take this off the board and bring this up to the top and continue with our inverse transformation. Okay, so that's where we're up to for now with our inverse Laplace. Now, we've got an inverse Laplace here with 10 over 3 times 1 over s plus 4 basically, and here we've got 1 over 3 times 1 over s plus 1. So now our inverse Laplace transforms, we need to look for a general formula. Now we usually have a table of Laplace transforms, and so this one here, basically if we look at 1 over s minus a, the inverse Laplace of that will become e to the a and t. T is usually a variable of time, but it could also be some parametric variable as well. But here, I'm just going to use t anyway. You can decide what you want to use t for. Okay, so that's our general solution for a Laplace transform of this format. Now we have this kind of format here, but we have these constants in front of it here, or coefficients. So now we have another general version of this, is where if we have a constant, where we multiply it, our result will be just the constant in front of it. So basically some sort of linear constant at the front, and then that would be c times e to the at. Now if the c was inside, so we had a c over the top there and not here, our result would be the same. We could just take the constant out and our result would still give us c times e to the at. Okay, so with that in mind, let's break this down now and solve our Laplace inverse transform for our f of s. So now we've got the inverse Laplace. So break these apart into two separate ones now. So we've got 10 over 3s plus 4 minus the inverse Laplace of 1 over 3s plus 1. Okay, now let's take these coefficients out. So then we've got 10 over 3, inverse Laplace now of 1 over s plus 4. We don't need the bracket inside anymore, do we? So let's just write it like that. And then the same for this one. So now we've got minus 1/3 inverse Laplace of 1 over s plus 1. Okay, now using these in this kind of format, for 1 over s plus 4, our a would equal minus 4, because s would be minus 4. And then this one, 1 over s plus 1, our a would equal minus 1. Okay, now with that in mind, let's plug them into these inverse transforms. So then we've got 10 over 3, and then using this, so our c is 10 over 3 for this first one, then we have e to the a, which is minus 4 in this case, and then our variable t. So that takes care of that. And now this one, we've got minus 1/3 e. Here we've got minus 1, and then our variable t. So I'm just going to write that as minus t. So we can rewrite this as well as 10 over 3e to the 4t minus 1 over 3e to the t. And that will be my solution for the inverse Laplace transform of this function f of s. Okay, that's it.